Yeah. All right, so again, welcome everybody. We are doing a Zoom a course today on ARINC-429 and ARINC-717. I'd like to introduce David Coppell, who will give the course. And if anybody has any questions during this course, please feel free to ask at any time. You can write me emails if you have any further questions after the course. I'd be happy to answer them. And if we could be of any help in the future, please let us know. And go ahead, David. I'll let you take over.
Okay. So we're going to talk about ARINC-429 today. We discussed it yesterday just very briefly, but you know, for those of us, you who were not there yesterday, it shouldn't make much of a difference. ARINC-429 has been in use since the 1980s on commercial aircraft. It is a commercial spec, as the name ARINC would imply. And it is a point-to-point interface. Okay, so this is an introduction to buses. We actually once had somebody who was working for us for several months, fortunately not on the technical end, who actually thought we had something to do with buses, as in school children buses. Anyway, I guess that's why the picture ended up there. Okay, starting with some terms that we did yesterday, now focusing more on the ones that relate to 429, which turn out to be Avionics bus, which only partially refers, because it's not really a bus. But source and sync are what's most relevant to us today, because source just means whoever's transmitting the data, and sync is whoever it is that's getting the data. Okay, again, this will be familiar for those yesterday, because it's a basic introduction to all of Avionics buses. So you've got different kinds of devices on an aircraft, those that create data, as it were, such as an altimeter. So an altimeter knows what the height of the aircraft is. How it knows is really the business of the altimeter manufacturer. You can use air pressure, you can use GPS, INS. There's a variety of ways of doing it, and we don't really care, because what we're concerned about with 429 is how you communicate the data. So assuming that you got the data, you now have to communicate it, and you're going to transmit it, which makes an altimeter an active device. A display in a cockpit, it gets the data from the altimeter, potentially, and displays it, so it's a receiver or a passive device. Black box people are familiar with, too much the last year or two. That's, again, a passive device. All it does is record data. And a flight computer will do both. Sometimes it'll get, sometimes it'll send. So that's just to give you an idea of who are the clients for Avionics buses. So on the first generation, there were no clients because there were no digital buses. Data was analog in nature, and it just wasn't transmitted. So if it's not transmitted, how do you know the altitude? The answer is the altimeter was a gauge. You looked at it, and that was it. It didn't go to anyone else. It was just the gauge itself was the entire device. In the case of a speedometer, everybody's familiar with those similar things. A compass is an extreme form of this, in which the needle is both the measurement device and the display device. That's an extreme case of a simple device. Now, the reason that we came to need digital buses was because of the next generation, in which a single data generator had to send the data to multiple places. The first place is still the display, because the pilot still would like to know what altitude he's at. And the second might be an autopilot, and a flight recorder could be an example of the third. I kind of made these things up, but they sound reasonable to me. An engine would have all of the same, plus a maintenance log, so that after you've flown for a month or two, you know how much work the engine has done. Does it need a full overhaul, a partial overhaul, and so on. Okay, so now these are the needs. So you've got one, in this case, one device transmitting and 3 or 4 devices receiving the data. And the way the simplest wiring, which is the way ARINC-429 will often work, is you just take a wire from the transmitter to each of the receivers. Theoretically, in 429, you could take the same wire starting from the altimeter and going first to the display, then to the autopilot, and then to the flight recorder. So a single bus with 1 transmitter and multiple receivers. That is legal under 429. It is not legal under 429 to have more than 1 transmitter on a bus, which simplifies things a great deal because there are really 2 issues from a technical point of view that you have to make decisions on when you're creating a digital bus. The one issue is how to make sure you don't have multiple devices transmitting simultaneously. And 429 handles very easy. You're only allowed to have 1. That's just the rule, 1 transmitter on a bus. So that simplifies that. The other issue is how do you distinguish between a 1 and a 0, right? It's known as the OSI level 2, the physical layer. That's its job, is to know how do you know what's a 1 and what's a 0, and we'll get to that later. Okay, just as a quick example of another option for wiring, instead of having everybody wired to everybody, so I have an example here of 4 missiles, each of which have to be connected to 4 devices, display, trigger, weapons test, and flight recorder. So in the wiring that we saw just a moment ago, point to point, this would require 16 wires. Whereas in this example, it requires 9 wires, right? These, the horizontal ones, this is 2, right? From the missile to this central vertical line. The central vertical line is the bus. Then you've got a missile attached to the bus, a display attached to the bus, and so on. So now you're down to 8. We've actually added a 9th, which is the mission computer, which I'll leave alone. The point is, instead of 16, you've now only got 8. Now, if I added 2 more missiles, for example, so then it would be 24 in the old way, and we've only gone up from 8 to 10 in the new way. So the more things you add, the more effective this is. 428 decided they didn't want to do it that way. Now, Firewire is another example of a bus used on the F-35, so it's like a very, very up-to-date military bus. And it neither does point-to-point like 429, nor does a single wire for the bus like 1553, but it uses a binary tree configuration. Just by way of an example of different ways you can do things. And ARINC-664 AFDX, which is based on Ethernet, has yet another method of working, and that most people are familiar with from their offices, that each individual computer that's attached to the internet is really first attached to a hub or a switch. And then that switch is in turn going to be, usually from your office, you'll go to a switch who's then attached to the phone company or to a satellite dish. From there, it'll go to the phone company side or whoever is running the satellite. And from there, it'll go on and on and on and on. But the point is that there's no problem with transmitting multiple simultaneously because everybody can transmit all they want. Switch has plenty of input ports, and the switch will forward them one at a time. I've got some information here which is not particularly relevant to us about Ethernet, basically. Okay, so and that's used on both new Boeings and new Airbus planes. Okay, so in short, there are many ways to skin the particular cat that is a digital bus. ARINC-429 is one of the simplest methods of doing it. Simple means inexpensive usually. On the other hand, if you've got multiple transmitters that have to talk to each other, that's not a good way to go. Fortunately, that's not what they needed on planes until recently. And now, newer planes that need more of that will use AFDX for the complex devices, but it will still use ARINC-429 and CAN bus, which is in the Avionics form ARINC-825 for the simpler devices. So buses are much simpler in terms of hardware because there are fewer lines. But they're much more complicated in terms of software because you've got to keep the collisions from happening and you've got to worry about the timing issues since everybody's sharing the same resource. Okay, so now let's get into 429 itself. What does the spec say? So first of all, who is ARINC? ARINC is an organization comprised of the major airlines and airplane manufacturers. Right. Right now, it was bought a couple of years ago by SAE, which is an organization, actually, Society of Automotive Engineers. Even though it has very little to do with cars. I mean, they do specs for cars too. But it turns out that the car manufacturers are so, years ago, they were the richest and largest companies in the world, so they tended to get involved in pretty much everything. Anyway, ARINC is an organization that pretty much only puts out specifications, because if they would actually try and sell anything, they would be a cartel, since they're made up of Boeing and Airbus and United and like pretty much everybody else who's important. So that's generally illegal in the United States if you sell stuff. So since they only sell documentation, they get away with it. Okay, anyway, ARINC's got hundreds of specs, I think, but ARINC-429 is the spec that is the most commonly used avionics civilian bus. Okay, now it itself was developed in the in the early 80s, and it wasn't developed in a vacuum. There was an ARINC-419 that came before it, and ARINC-419 had like a dozen different sub descriptions of buses. Most of them had in common that the major way of moving data was through a 32-bit word. They had multiple different speeds that they worked at, and some of them used 2 wires, some of them used 6 wires. There were all kinds of little differences between them that made it difficult to put together an airplane, because everyone was a different spec. So ARINC-429 was an attempt to kind of merge these things together and give instructions to equipment manufacturers how to do something that would be able to interact with other people's systems. Okay, so it's a point-to-point bus, which basically means that the wire goes from the transmitter to anybody that needs to receive it. Now, you could have multiple outputs from a single device, or you could have one output that's just strung along serially from one receiver to another. Okay, message format, or once we've determined how we keep you from colliding, which is by only having a single transmitter. So the data itself for ARINC is sent in 32-bit words. So ARINC-429 is not really designed for sending large amounts of data. There is, in fact, a part 4 of the spec that talks about Williamsburg protocol, which does allow you to send files, but ARINC really is not an efficient way to send files. And we haven't come across a lot of people who use Williamsburg. Now, so you're sending a 32-bit word at a time. Each word represents an engineering unit. So altitude has a word, latitude is a word, longitude is a word. And usually you're not going to really have you might have an engineering unit plus a discrete or two. You won't have more than one engineering unit. And actually we'll understand why shortly. Okay, so what is if all words going out on ARINC are 32-bit words, then what does a 32-bit word look like? And the answer is it looks like this. It's got 5 subfields. The label subfield, the parity, SSM, sign status matrix, the data itself, and something called an SDI. So between all of them, we've got 32 bits. The numbering in ARINC, for some reason, goes from 1 to 32, as opposed to the way most software people think, which is 0 to 31. Something to keep an eye on, because different specs do things differently. Okay, so now let's discuss each of these subfields individually. So the label, which is always the first 8 bits sent out over the bus, since it's 8 bits, it allows for 256 different possibilities. And what these possibilities are the kind of data that we're talking about. So if you want to be able to interpret the data, you have to do it according to the label. So for example, altitude is going to be a particular label number. We'll actually see which one in a minute. So by knowing what label it is, you know what kind of data we're looking at, and you know the format of the data. All of this is written into the spec. Now, because there are only 256 possible label values, and airplanes might have more than 256 different kinds of data, so we reuse labels. Because it turns out that any particular piece of equipment does not require more than 256 labels. So, however, the labels needed by an engine are significantly different than the labels needed by landing gear, which are themselves significantly different than the labels needed by an inertial navigation system. So each one of these things, inertial navigation system or landing gear or an engine, are called an piece of equipment and have their own ID. So according to the equipment ID, you now can reinterpret the labels. So label 100 on equipment ID 7 might be different than label 100 on equipment ID 12. The equipment ID itself is sent in label 377. If you don't really have to send it, because presumably the receiver attached to you knows who he is and knows who he's attached to. The equipment ID will be the equipment ID of the transmitter. But you know, a receiver knows that he has to be attached to an inertial navigation system. If you attach him to landing gear, he's not going to work. Now, one odd thing that comes up is why is the label called 377 if there are only 256 possible labels? The answer is that in their infinite wisdom, the ARINC people decided that labels should use octal format. For those of you not familiar with octal format, each digit is permitted a value from 0 to 7. After you get to 7, then you go to 10, which is an 8. In other words, the 1 digits mean what they say. A 5 is a 5, a 7 is a 7. The second digit over is you take that number and you multiply it by 8. And the third digit over you take and you multiply it by, I guess, 64. And so I'm not going to do the math, but 377 turns out to be 255 in decimal. Okay, so now here are some examples. Label 372, which is the octal representation. If it is on an altitude and heading reference system, is going to be wind direction. However, if it is on a GE control system, equipment ID implies GE engine control system, then is a fan speed. So there's absolutely not the slightest connection between wind direction and fan speed, just a reuse of the label. Okay, and the label is the first thing in because there's not much you can do with the rest of the data until you know what label it is. Okay, so the label is the first of the 5, right, of the 5 subfield of a 429 word. Now we're going to jump to the right side, and this has to do, why am I jumping to the right side? Because it's 9 and 10. Label is called bits 1 through 8, and the SDI is bits 9 and 10. So why is it that in my picture on the top, I first have the label, which is 1 to 8, then the parity, which is bit 32? It seems counterintuitive. Well, it is counterintuitive, but that is the way the data is sent out over the bus. The first thing sent out is the label, then the parity, then the SSM, then the data, and then the SDI. So they decided to just switch the order, right? In addition, the label is sent out bit 1 through 8, and the other thing is low to high, and the other ones are sent high to low. Anyway, this matters only if you're looking at an oscilloscope, which we'll learn how to do later. But be aware that on an oscilloscope, you got the label first and then the parity. Pretty sure. Okay, anyway, the SDI is there in case you have, in fact, connected a single transmitter to multiple receivers. So let's say you've connected the transmitter is a flight computer, and it is connected to the landing gear. Now, landing gear typically comes in threes, right? You got 3 sets of wheels in the landing gear, and you need to transmit data to all 3 of them. Now, I don't know if you transmit the same data to all 3 of them. Could be that you want the rear, right? It's typically a tricycle configuration, right? So you got the 2 rear and the 1 forward. Maybe you want the rears to go down first. I think they're larger. Maybe they take more time. Who knows? So you might want to send something just to those 2, or you might want to send something to all 3. The SDI allows you to do that, even if your wire connects directly from your transmitter, your flight computer, to all 3. Right, and there's not 3 separate wires, but 1 wire going first to the first landing gear, from there to the second, and from there to the third. By altering the SDI, you can alter which landing gear listens to you. So we'll assign them numbers, right, 0, 1, and 2. And if its SDI is 0, it'll go to the first one. If it's a 1, it'll go to the second one, and so on. If it's a 3, that's a broadcast. It'll go to all 3 simultaneously. Now, if you don't happen to connect yourself to multiple receivers on a line, then you don't need the SDI. And if you don't need the SDI, then you can just, you see it's contiguous with the data. Data goes from 29 down to 11, and this is 9 and 10. So you can just make the data go from 29 down to 9, giving you, instead of 19 bits of data, 21 bits of data. And there are labels that do that. Okay, the data itself is, as I said, either 19 or 21 bits, depending on whether you have an SDI. And it has to be, it's interpreted according to the spec. And there are a number of different possibilities. But once you know which label it is, you know which possibility you're using. Now, what the possibilities are binary. And if it's binary, that means that it, like any binary thing, it'll have a sign bit as its top bit. Which will be, we'll see, bit 29. And then following that will be the data in standard binary format. If you don't need all the bits, then the low order bits will just not be used. But it'll always start from the top, from 29, and work its way down. BCD is binary coded decimal. And we'll see an example of this, but binary coded decimal means you take a bunch of bits and you stick a value from 0 to 9 in them. Right? So even though if you had 4 bits, you could theoretically go up to a hex F, which is decimal 15. But because it's decimal coding, we're not going to give it a value greater than 0 to 9. So dates typically will use this kind of encoding. Discretes could be a single bit that just means on and off. And that will be in addition to the BNR or the BCD value. You could theoretically have a label with only discretes, but you're also allowed to have a label where you use the, let's say the binary value will only need from 29 until 15. So we said we're not using the lower ones. You can use them for something else, for a discrete. You can't use them for another number because they have no sign bit. There's only 1 sign bit, and that's 29. And there's another type of data called ISO alphabet number 5, which is used for alphanumeric data. If you want to send strings, you can do it that way. Okay, actually, as always, I forget that the next slide says what I was planning to. Okay, so BNR data is a contiguous field. The sign bit is always going to be in bit 29, and then the high of the magnitude bits will be in bit 28. So, for example, if we want to have values from 0 to 32,000, that needs 15 bits, which means that we'll use from bit 29, 15 bits down. Or, yeah. Okay, now within the spec, it tells you not only it tells you the number of bits, it tells you the units. Now, are we talking about knots? Are we talking about pounds? Talking about degrees? Are all examples of units of engineering data. And here I give an example, label 366 of equipment ID 4. Remember we said before, in order to positively identify something within the specification, you need to both the equipment ID of the transmitter, the source of the data, and the label. So equipment ID 4, label 366 is knots are the units, and it has a range of 0 to 4096. Plus it has 15 significant depth. All of these fields are in there. Now, the immediate question, jumping to your head, is if we just said that 15 significant bits gives us 32,000, technically 32,767 possibilities, then why is the range only 0 to 4096? Why isn't it 0 to 32,767? It's actually 30,768 possibilities because 0 is a possibility as well. Okay, and the answer is because if I did that, then the precision, or the, not the precision, the resolution would be a knot. But the people who wrote this spec decided that they want the precision to be better than a knot. They want it to be 1/8 of a knot, which in decimal is written as 0.125. And therefore, they need 8 times as many bits as they would need if it was just a knot. And so they only can have a range of 0 to 4090. It's actually 0 to 4095, but a range of 4096 possibilities. So we've got in the spec the number of bits, the resolution, and the range, and they all have to fit together. Right? And as if I had said that I'm only giving you 12 bits with a range of 0 to 4096 and a resolution of 1/8, that would be impossible. So you have to check the spec, and I'll show you later. It's really important to check the spec because they sometimes lie a little bit. Because that's binary data. BCD data uses 4 bits per decimal digit, unless you know that the range of the decimal digits is smaller than 0 to 9. For example, on a date, so the low digit has to be 0 to 9, but the second digit for days of the month, the only possible values are 0, 1, and 2, so I can make do with only 2 bits for that. Another example, label 10 is present position latitude. This is in BCD, has a range of -180 to +180, and a precision of 0.1 minutes. We'll see what this actually means in terms of what it looks like. Okay, so now we have for the BNR, we said that there's a sign bit. Turns out for BCD, there's also something equivalent to a sign bit, but it's not entirely fair to say that it's a sign, because there are times that plus and minus are not the natural values to talk about. So if you're talking about latitude, then latitude really means there's north latitude and south latitude. It's not really plus and minus. And longitude is east and west. Again, we can assign minus to one of them, but it's not that natural. So you can also just call it north and west. And this is particularly because in BCD, as opposed to binary, binary is 2's complement. BCD is always sign magnitude, so that a +2 and a -2, in BCD look exactly the same. You have a different sign bit. The SSM tells you whether it's plus or minus, but you've got a 2 in the rest of it. Whereas in binary, +1 is a lot of zeros with a 1. -1 is all F's. So there's that's called 2's complement, and it means that it's not that you just got the sign and the value. That's called sign magnitude. That's what BCD is. Binary is different. Okay, so now let's look at an example of BCD data. We just said that that label 10 is degrees. and it's accurate to the 10th. The precision is a 10th of a degree. So if you want to show north 75 degrees and 59.9 minutes, then the way you would display it, these are the bits that are available to us in binary, and underneath the binary, I rewrote them in hex. So you've got a 75599, and we know when we read this that we have to put a decimal point before the last digit. So the first two digits, 75, are the degrees, the next two digits are the minutes, and the last digit is tenths of a minute. In order to do this, we need 21 bits, and therefore you can't have an SDI in a value that's taking this particular label. Okay, discrete is on-off, landing gear up, landing gear down, that kind of thing. And if it's landing gear up or down, it might be landing gear talking to the flight computer. And one thing that we see on 429 devices, they very often have quite a few 429 ports, some input, some output. So the same device that's getting data from one guy might be sending data either to the same box, like the flight computer, or possibly to a different box. Certainly when you get into something like inertial navigation systems that are very central to the flying of the plane, they could be connected to a lot of different things. Okay, and the ISO alphabet is ASCII strings, as we said. Okay, the SSM now is the only field we haven't spoken about. We talked about the label and actually we didn't talk about the parity. Okay, we talked about the label, the SDI, and the data. Now we're on to the SSM. And the SSM is 2 bits that, right, so there's, sometimes they refer to a third bit as an SSM, but that really is a sign bit or a north-south bit, as the case may be. The 2 highest bits of the SSM, 31 and 30, are used to tell you whether the data is worth anything. Right, so there are 4 possibilities, and because it's 2-bit SSM, and the 4 possibilities translate into a valid data, which turns out to be 1 and 1, or not valid data. There's actually not, and data cannot be valid for 2 possible reasons. Either because we haven't gotten any updates, right? This is the piece of equipment transmitting to the other side, and we'll see that it has to transmit periodically. So each label is told you got to transmit, let's say, every 50 milliseconds. Okay, but let's say 50 milliseconds have passed since the last time I sent data, but I haven't gotten any new data, right, from my altimeter. Think of the altimeter as being 2 parts. There's the part that knows how to measure altitude, and then there's the part that transmits data. And these 2 parts are connected to each other, but they're not the same thing. So the part that's transmitting the data is waiting for the part that measures altitude to tell it something, and what if it didn't? So then it can send another value in the SSM to say, look, the last data you have is the best I can do. I'm not sending you anything new. Alternatively, let's say the altimeter broke. So the SSM now can be used to say, don't count on me. This data is just garbage data. It's not that it's not new, it's that it's actually garbage. And the 4th possibility is a test mode, which is presumably not used in flight. Okay. Right. Okay, so that's SSM, and now we'll move on to parity. For those of you not familiar with parity, I'll give it a 20-second introduction. There are 32 bits in this word. 31 of them are what we've discussed until now, the label, SSM, data, SDI. And we would like some way of letting the receiver feel good that the data that was transmitted is the same as the data that was received. Because there are noises in life, and there are electrical noises, lightning can come nearby, there's all kinds of reasons why data might be a little bit messed with. So what we do is we say, well, all right, well, we've got 31 bits so far, and those 31 bits are either ones or zeros. Let's count up the number of ones. If there are an even number of ones within those 31 bits, then I'm going to write a 1 to the parity bit. If there are an odd number of ones, then I'm going to write a 0 to the parity bit. And that way, if you count up all the ones, you're guaranteed, and count up all 32, including the parity bit, you're guaranteed to get an odd number, which is why it's called odd parity. Now, the advantage of this is, if something messed with one of the bits and changed it either from a 1 to a 0 or from a 0 to a 1, that's going to change the parity. And the receiver is now going to know that this data is not valid, that something happened to mess it up. I don't know, it changed a bit. Now, this is not a perfect way of knowing that nothing went wrong, because if 2 bits are changed, the parity will remain the same. But the likelihood of that happening is astronomically small, so we satisfy ourselves with a single parity bit. There are things called Hamming codes, which are ways of doing more complex checking. There are also CRCs, but it's not relevant if your entire message is only 32 bits. Okay. Fine, so now we finished discussing what the word looks like, and every word that goes out on ARINC-429 looks exactly like what we've described until now. Every single word has got 32 bits, including a label, including parity. Well, those are the things that are guaranteed, but, so now within that, you can still show all kinds of different data: latitude, longitude, air pressure, roll pitch, yaw, roll rate. There's a lot of stuff that you can do, all done in the same 32-bit format. Okay, so now let's get away from what we're sending and talk a little bit about the timing of sending it. So there are 2 speeds defined in ARINC-429, and this is a holdover from the 2 popular things that were in ARINC-419 before that. And the speeds are what we call high speed and low speed. High speed is 100 kilohertz, which is 10 microseconds per bit. And low speed is 320 microseconds. And low speed is 12.5, which is 8 times slower than that. So it's 80 microseconds per bit. Now, since a word is, of course, 32 bits, so 10 microseconds per bit translates into 320 microseconds for a full word, and 80 microseconds per bit translates into about 2.5 milliseconds. In addition to the time that the word takes up, the spec defines that it would be a minimum of 4 bit times dead time on the bus between labels. So you're not allowed to send labels out contiguously. Which means that really, if you want to know the maximum throughput, the maximum number of labels that you can send per however amount of time, so for high speed, you divide that time by 360 microseconds, and that tells you the number of labels that you can send out. So for instance, if you're interested in knowing how many labels you can send out per second, so you divide a second by 360 microseconds, and you, well, whatever it is that you get up with. Roughly speaking, that means you can get 3 per millisecond, which means about 3,000. And low speed, it's an eighth of that. Okay, which would be about 375. Okay, so that is the frequency of the bits, right? That's the speed of the bits. If you're looking at an oscilloscope, that's how you know what a single bit is. There's also a frequency of how often do you send a label, which is a totally different animal, right? Because I can send, I know that a label itself at high speed is going to take 320 microseconds, but now I have to ask, do I send it once a second? Do I send it 10 times a second? That's the transmit interval. Now, typically, and in the spec, there is a table of all of the labels that are defined in the spec. And for each one of them, it tells you how often you should send it out. Now, it tells it to you in a range. It has to be at least 25 milliseconds and at most I'm sorry, at least 50 milliseconds and at most 25 milliseconds. Smaller is more frequent. So then 25 milliseconds is a reasonable amount of time, which translates into 40 times per second. And that would be one of the faster labels. And the slowest label that you generally come across is once per second. Obviously, there are, and this is for, well, time data, obviously. You're going to send once per second because the clocks are accurate only to a second anyway. There's no point in doing it more often. And there are other labels which, frankly, you don't have to send at all, or you can send once, like the flight number. You're certainly not going to send it more than once per second. It doesn't change during the flight anyway. Okay, so now this is what the spec, well, kind of what the spec looks like, and there are a whole bunch of pages of this for each, and they're ordered by label number, right? So you start with label, I don't know if there's a label 0 or label 1, and then within label 1, it'll tell you 5 different equipment IDs, all of which support label 1. Now, some labels will have only 1 equipment ID, some might have 10. That's the way it's ordered in the spec. Okay, so for each label and equipment ID combination, there's a bunch of stuff I need to know. So the name is something that I'm curious about. It's not actually used on the bus. That information is not sent over the bus. It's just something that the transmitter and the receiver both know. In fact, all the rest of this information, that's the reason it's written in the spec, is things that the transmitter and the receiver both have to agree upon in order for the receiver to be able to properly interpret the transmitter's data. So the first thing you want to know is, what is it that you're sending me? So it's fuel quantity. And what are the units? So the units are in pounds. Now, a tenth of a pound is still, the unit is still a pound. The tenth goes into resolution. So the range is and range is done in different ways. In this case, range obviously means from 0, because you can't have less than 0 pounds of fuel, up to a maximum of 131,000 pounds. Okay, and the number of significant bits. How many bits should you interpret when you get the 32-bit label? How many data bits are there? And the spec tells you there are 15. Now, 15 data bits, we've mentioned a couple of times, gives you 32,768 possibilities. Well, how do I get a range of 0 to 131,000 pounds if I've only got 32,000 possibilities? And the answer is that my resolution is 4, meaning a 0 in raw data means 0 pounds. A 1 in the raw data means 4 pounds. There is no way to represent 3 pounds, because that's my resolution. And therefore, a 32,000, right, 32,767 is in fact going to represent 131,000 pounds. Okay, and the interval, in other words, how often is this label supposed to be sent, is between 500 and 1,000 milliseconds, or in English, between half a second and a second. And the reason is clear. You don't burn that much fuel in a second. So there's no advantage to my getting it more often than that. And if you are burning more fuel than that in a second, the likelihood is that the pilot's going to figure it out without us telling him over the data bus. Okay, so now this is an actual example of a digital fuel gauge system on an Airbus 310. And that means, because we said the resolution is 4, that if you read the value, the data value of the label, and it says 10,000, what it really means is that there are 40,000 pounds of fuel in the engine, well, available to the engine. Okay, now let's, right, we said before 10,000 in there, but we didn't show you in binary. What does that look like? What does 10,000 look like? So now we will see. Let's see. And now I'm not describing the label in this picture, because we said the label is whatever we said the label was. What we are describing is the data, right? All the D's that you see here are the data. In fact, I have some toy that I'm supposed to be able to play with here. Let's see, change pen color, and we'll make it yellow. It's kind of yellow. Okay, so the data is these guys. Whoops, all right, I'm not doing this very well, but that's the data. And as I'm looking at the data, I see this is the binary, this is the bits, and this is translating it into hex. So 0 and 0 is a 2. And I get a 2710, and 2710 actually lied because really this is supposed to be 0 and this is supposed to be a 1. I need to fix that. Anyway, let's assume that it says 2710, which is the hex equivalent of 10,000 decimal. Now, the other interesting to see is that here you have 3 capital P's, right? And these 3 capital P's represent pads. In other words, I really have available to me more data bits, but I don't need them because I only need 15. So those 3 are not being used. Now, we had said that there were really 19 data bits. So the 19th is the sign bit, which I also don't need here because there's no such thing as negative fuel. So this is an unsigned integer. I don't need the sign bit. I don't need the pad bits. This is the parity bit, and you know I do need it, but I'm not interested in it for purposes of this discussion. Okay, another example of reading the spec is roll angle. So roll angle is labeled 325 under equipment ID 4. Now, the other thing that you know from the spec, by the way, is it a BCD or is it a BNR? Turns out that in the 429 spec, you've got like 6 pages of definitions of labels and equipment IDs for BNR, and then another 6 pages of labels for BCD. So by knowing what page you're looking at, you know whether it's a BNR or a BCD. Okay, so now we're looking at another one, roll angle. Roll angle is degrees. And the range is from minus, well, technically minus 179.999 degrees till plus 180 degrees. Significant bits is 14. So 14 gives us 16,000 possibilities. And the resolution is 0.01. Okay, so what I want to point out over here is in the spec, and this is taken directly from the spec, and the spec in fact says 0.01. However, as I mentioned before, there's a relationship between the different fields here, the significant bits field. So 14 bits gives you 16K values, right? 16K meaning 16,384 potential values. And these values are going to be spread between 0 and 180. Okay, so clearly I get more than one value per degree, because I only need 180 values to give me one value per degree, and I have a lot more than that. Okay, so how many more? So I divide 180 by 16,000, and that tells me the precision of each bit, or the resolution of each bit. Okay, well, if I do the actual math, I see that the resolution is 0.0109863, whereas what the spec said is that it's 0.01. Now, the spec said it because they were too lazy to give more than 2 digits. But in fact, if you want to be accurate, you really want to use all of those digits. So don't trust the spec on the resolution. Figure it out yourself if you're working with it. Okay, so what is resolution? Resolution is the range, 0 to 180, divided by the maximum number of values. Now, maximum number of values depends on the number of bits, and the math of it is 2 to the order of the number of bits. So 2 to the 14th is 16,384. And these are the formulas which most of you are absolutely not going to be interested in, so I'm going to move on. Okay, so now here's another label. And this label, so what do I know about this label? So I'm telling you that this came in as label 325. because on the picture on the top, I've only shown you bits 32 through 9, so I left out the label number. So take my word for it, it's label 325. And the rest of the data, not counting the label, or actually even counting the label, yeah, is 53DC7, which is a completely meaningless number, because that includes the parity, and it includes the SSM, and it includes the everything. Okay, so that's not helpful. So what I really want is just the fields that have D's in them. And so I did that for you here, and I show you that the D's, if I divide them into hex, so I start from the lower, these are the low 4 bits, that's a 7, the next bits are an F, then a 4, and then a 1. That's how you put them together. Sorry, not up to that yet. Okay, so now I've read, and I know that this is called the raw value. The value that came in with the label after I isolated just the data portion is now called the raw value, which is a 14F7. In decimal, that's a hex value. In decimal, it's right because this is a binary label. If it were a BCD label, it would be in decimal, but it's not. So its value really is 5,367. We saw in the previous slide that the precision, is that precision? Yeah, the per bit value is 0.01, whatever it is. So we multiply 5367 by that number, and we end up with 58.96 degrees. Now here you can see why it's important not to trust the spec, because if we had multiplied 5367 by just 0.01, we would have ended up with 53.67. But the real value is 58.96 because it's not 0.01, it's 0.010986, which is, when you multiply it by a large enough number like 5,000, it turns out to make a difference. Okay, fine. So now we've seen what a word looks like in ARINC-429, what the individual bit fields are, how to read the specification, how to read the bits, how often to send the bits, which is, pretty much what you need to know when you're dealing with ARINC-429. But I do want also to show you what it actually looks like on an oscilloscope, in case you ever have to look at an oscilloscope. And it also gives us an opportunity to answer the second question that I posed at the very beginning that you have to answer when you're writing a spec. First question is, how do you prevent multiple transmitters from transmitting simultaneously? The second question is, how do you distinguish between a 1 and a 0? On a digital bus, that's pretty important. Okay, and the answer is on this is a picture of, from the red arrow here until we get till this dead area here. That is a single ARINC-429 word. So there are 32 bits here. And if you count up the guys that are going up and the guys that are going down, in fact, let's do it. I see the groups of 6 are, the first 3 are groups of 6, so that's 18. Then a group of 5 is 23. On the bottom, we've got a group of 4 to 27, 2 groups of 2, which brings us to 31, and then a single, which brings us to 32. So we've got 32 of these spikes, some going up, some going down, and each one represents a bit. So as you might expect, going up is one thing and going down is the other thing. Now it turns out that there are 2 wires in an ARINC-429 spec, and the wires are complements of each other. So on one of the wires, up means a 1 and down means a 0, and on the other wire, up means a 0 and down means a 1. So you're better off knowing which wire you're looking at if you want to properly interpret the data. Anyway, that's what, on the scope, that's what it looks like, so you can see exactly what all the values of all the bits are. You also, so some of the things that you check for if you're on a scope is that this gap over here, right, has to be minimum of 4 bit times. There should be exactly 32 bits. And if you measure the time, Right, you see here, this is 50 micros up here. It says that it's 50 microseconds per box. So if we count the boxes from the left, you've got 1, 2, 3, 4, 5, 6, and a little, or about 6.5, a little more than 6.5 actually, if you go till here. 6.5 times 50 is 300 and is over 320. Right, 6 times 50 is 300, and then what's left? So that's the other thing you want to check. Is this tells me immediately that this is a high-speed bus, 100 kilohertz, because otherwise it would be 2.5 milliseconds per a word. So I know that it's high speed. I can count and see that it's 32 bits. I have a reasonable space in between the two words. Everything looks happy. Obviously, I haven't tried to interpret what the data is. That's really not something that one does on an oscilloscope. That's what software is for. Okay, so to summarize, we have seen the structure of an ARINC-429 word, the 5 fields and 32 bits. We've seen coding mechanisms, binary, BCD, ISO alphabet number 5, discrete. We've talked about frequencies of the hardware, 100 kilohertz or 12.5 kilohertz, and the intervals of the labels. Typical range 20, 25 milliseconds on the faster side to a second on the slower side. Okay, now, how have we implemented this at Excalibur? So these are some of our products. That's the 4000 PCIe on the left, the UNet on the right. They both do the same thing, except if you happen to have a PCIe interface in your computer, you'll use the guy on the left. If you have if you want to work with Ethernet or USB, then you'll use the guy on the right. And, well, as an example, what kind of things can you do using the software and firmware that, with these tools? So when you're receiving, since, as I mentioned before, a lot of equipment pieces have multiple channels. So you might be receiving from a bunch of different places. Or you might be integrating a system and you want to see data from a whole bunch of different places. So let's say I'm receiving from 8 different devices. So I can look at the data in a couple of different ways. The first way is to say, well, listen, I'm thinking of this as a whole. I'm not looking at 8 different devices. I'm looking at the way my airplane operates. And so every time a message comes in from whatever source, any of the 8 buses, I'm going to put it into the same buffer. And in that way, I'll get a picture of the timing and the relationships between data from different data sources. That's one way of doing it. A second way of doing it is saying, you know, I don't really care about the relationships. Each guy is in business for himself. And I'd like to have separate buffers for each of them. So that's called sequential mode. We can do that as well. And then there's a lookup mode that says, not only am I not interested in relationships between different channels, I'm not even interested in the relationships between different labels on the same channel. I just want to know the most recent data for each value. So if you want to show a cockpit-like display, and on the display you only see the latest data, so that'll be lookup mode, where each label gets its own buffer, and you don't have a history. What you have is the most recent data. On transmission, so there are also a number of possibilities. First of all, you can group labels into messages. So you have a whole bunch of messages that go out 10 times a second, and other messages that go out once a second, and other messages that go out at whatever rate that you choose. And within that message, you can also put gaps in between the words. Minimum, of course, is 4, because the spec says you need 4 bit times between words, but you can have longer periods of time if you want. You can inject errors so that that'll test the receiving device to see if it handles errors properly. Because on an actual airplane, errors happen. I know nobody's flying these days, so I don't mind saying that. Okay, now in terms of the timing, so there are 2 ways you can do it. According to the spec, it makes sense to say, all right, this label goes out at this frequency. That was 10 times a second. However, that takes away control from the user, gives it to the card, which means that the stuff will go out extremely accurately. But it also means that you may not know exactly what order the labels are going out in. For example, if you have label 10 is going out 10 times a second, and label 5 is going out 5 times a second, so occasionally they're supposed to go out at the same time. Well, when that happens, which one goes out first? Well, it's up to the card to decide if you're in frequency mode. On the other hand, if you want complete control, then you can say, you know what, I'm going to make my own bus list, and I'm telling you, send label 1, then 7, then 10, then 5, then 1 again, then 5 again, and etc. And this amount of time between each label, it doesn't have to be the same amount of time. So I can send label 1, wait 2 milliseconds, send label 5, wait 6 milliseconds, send label 10, and so on. And that way the user has total control of what's being sent out. And then, you know, depending on your test needs, one might be better than the other. Okay, FIFO mode, it was something that a customer actually asked us to add. It wasn't in the original card, but he said, all right, I want a FIFO, and this FIFO is going to be things that are being sent out every 20 milliseconds, but I'm not sending the same thing every 20 minutes. I'm going to give you 10 values, and every 10 milliseconds, send the next one. Okay, I'm not going to spend much time on it because I'm not really sure why he wanted it, but he did, and I really give it more as an example of the fact that if you have custom needs and we can help out, ask. We've done it before, we'll do it again. Translation mode was another thing we did for a specific customer. He had 2 pieces of equipment that apparently they used to talk to each other. And then one of them got upgraded, and it was changed a little bit. I don't know what exactly was changed. It might have been that the SDI was changed, or something was changed in the transmitter. And really, the receiver should have been changed to handle the new protocol, but he didn't want to change the receiver because it was working perfectly well. So he asked us to translate. He said, whenever you get this in, send it out, but send it out with a different SDI. Or send it out with a different label, or do all kinds of stuff to it. So we made a generic kind of a translator, which takes something in and gives you a whole slew of different options for how you might want to change it. Now, this is useful for changing things at a very localized level per label. The Mac, which is another product of ours, which I think we'll get to in a minute, is much more serious kind of translating. We'll talk about it. In fact, here it is. So there, what we talked about a minute ago was translating ARINC-429 to ARINC-429 with just a tweak. But what if you got say a helicopter, which has been built completely with 1553, military helicopter, everything in it is 1553. And one of the boxes in it has gone obsolete, and you need to upgrade to a different box. Now, in order to upgrade to a different box, you got a lot of stuff to worry about, right? It's got to fit in the same space, right? So that's form. Form is the shape, and it has to be the right size and the right shape, and it has to take the right power that's available over there, and it's got to do what you want it to do. It's got to have the correct information, power dissipation. There's a lot of requirements for this box. Let's say you found the perfect box, but it's not MIL 1553. It's everything else is right, but it speaks serial or Ethernet or 429, and apart from that, it's perfect. Okay, well, in the old days, that would that's sort of like asking, no, let's not use that. Okay, it would be useless basically, because perfect means perfect. Perfect doesn't mean speaking a different language. However, those days are gone, because the Mac can take in, let's say it's serial, from the new device, translate it into 1553, and then send it on to the rest of the helicopter. So as far as the helicopter is concerned, this new device is a 1553 device. As far as the device is concerned, this helicopter runs on serial. And neither of them care because we're there in the middle translating. So this obviously is much more complex than 429 to 429 because it's completely different protocols. The hardware is different. What defines a bit as a 0 or a 1 is different. The frequencies might be different. One of them might use gallons and the other one uses liters, or tenths of a kilometer and half of a mile. All of these are things that the Mac can handle, and neither side will be aware that it's actually talking to a device that has no concept of its language. Okay, so now talk about ARINC-429 does not work in a vacuum, or at least not anymore. It used to be pretty much the only game in town on civilian aircraft. Today, the larger aircraft are using AFDX, which is Ethernet based, or they're using CAN bus. And so you've got some devices that are CAN bus, some devices that are AFDX, and some devices that are ARINC-429. And there are various reasons why you would use one more than the other. And therefore, you need to translate between them. That's exactly the sort of thing that a Mac can help with. Okay, that's it for the 429. I believe we're supposed to be doing 717 as well. So if you want, we can break for a couple of minutes or go straight into it. Open to suggestion. Meanwhile, I'll set up the next slideshow.
Any questions?
Yeah, well, this is Sergio Gomez from Excalibur. Yeah, from our side, we are interested in have more details about the Mac converter. We are going to need some kind of converter from going to possibly from a serial port or Ethernet to a CAN bus. So we're interested in that product and also to know which are the environmental ratings that this device could provide. I mean, yeah, the typical temperatures and yeah, the environmental ratings that this device is tested.
We do have a CAN bus presentation if you're interested.
Okay. Yeah, that would be nice to have.
Okay, so just Chaim will set it up.
I will. You have everything.
Okay.
See, people do laugh at your jokes.
I want it in real time. That's why I don't want you to turn off the mic. Actually, maybe it's why I do want you to turn off the mic. Okay. Anyway, ARINC-717 is also used on commercial aircraft, but it's used for a very specific thing, namely for flight data acquisition and recording systems, which are very closely related to black boxes. The idea is you want to gather data from all over the plane, compress it into a single data stream, and then send it on to the black box. So the black box reads ARINC-717, and there's a data concentrator which writes ARINC-717. Okay, so the data acquisition unit is generally going to be in the cockpit because that's where most of the avionics are, and its job is to gather data from all of the avionics buses, right? Which there may be, well, not necessarily all, but a lot of them. And then it is going to write them to the flight data recorder, which is also called the black box. I got a picture of one. As you can see, it's not in fact black. And it's usually in the rear of the plane. The reason is because planes don't get rear-ended a lot, and therefore it's the safest part of the plane. tendency is if planes are going to crash, they're going to do it from the front. Okay, and the black box you want to survive, apparently more than the passengers, so you put that one all the way in the back. The reason that it's orange is because by the time you're looking for it, it's hard to find. So they want it to be a bright color. Okay, so what kind of data do you record? All kinds of stuff. Position certainly is a good one. Heading, acceleration, landing gear, flaps, basically all the information that the guys in charge of figuring out why your plane went down need in order to figure out why your plane went down. Now, every aircraft is going to be different in terms of what data is most critical, and therefore, every aircraft is going to decide for itself what data to put into onto the black box. Now, in terms of logically speaking, the 717 data is collected in frames. A frame is 4 seconds long. So all the data collected is collected every 4 seconds. Now, that doesn't mean that nothing is collected more often than that, but if something is collected more often than that, that just means it's available in multiple places within the frame. So there are 4 subframes, which are 1 second apiece, and together they form a frame. And within the frame, in other words, within the 1 second, it's divided further into a bunch of words, each word being 12 bits. 12 is a very strange number, but that's what they picked. Okay, so now if I know what frame I'm in, and I know which subframe I'm in, and I know that I'm in, say, the 32nd word of the subframe, starting from the 9th bit, I know exactly that's going to be altitude. Usually it always starts from the first bit, but in theory, an engineering unit doesn't have to be 12 bits. You'll see that, in fact, it could be more or it could be less. In addition, within a single vertical acceleration, which, you know, how fast you're climbing, you would think would be very important if something goes wrong to know that information. And therefore, we're going to record that maybe every 30 milliseconds. Whereas the flight number, we really, you know, obviously don't need to record it at all because, you know, when I'm looking through the pieces of aircraft floating at the bottom of the sea, you know, one of them is going to have the flight number on it, and how many flights went down over there anyway. In any event, let's assume we do put it in. We'll put it in once a frame. Okay, so landing gear position only needs 1 bit. Latitude, depending on what precision I want, will need probably 24 bits. So the 12 is just the size of a word, not necessarily the size of an engineering unit. Okay, so on a scope, there's no beginning and no end, right? We saw in 429 that you had a word and then a space and then another word. That doesn't exist in 717. 717 is just constant bits. So by looking at it, you'll never know where a word starts and where a word ends. And in fact, even hardware has a tough time doing it. And the way it does it is very interesting, actually. Each subframe, a subframe goes out once per second, and there are 4 of them. Each subframe starts with the same number each time it goes. So the first subframe always goes out with an 1107, and the second subframe always goes out with a 2670. So over the course of time, you'll see these numbers repeating themselves. Now, when you see all of them in order, so what happens is you start your card running, and the hardware of the card looks at each bit, and in each bit it checks each set of 12 bits, and it says okay. And remember, I don't even know where the beginning and the end of a word is. So the first bit that comes in, it reads from there the first 12 bits, and it says, "Are you in 1107?" And if it's not, it throws out the first bit, adds the 13th bit, and now looks at this set of 12, 2 through 13. It says, "Are you 1107?" And so on. Eventually, it'll find an 1107. Now, it might take up to 4 seconds, because if it got connected to the bus just after the 1107, it's going to be another 4 seconds till the next one comes along. Okay, so it now says, okay, I got you. I see an 1107, and it continues reading. And this time, it's looking at bits and asking each bit, are you an 1107 or a 2670? And I have to ask both of these questions because it could be that 1107 happened to be the value of data, and it wasn't really the beginning of the subframe at all. So I can't trust the fact that I found an 1107 that this is now the beginning of the frame. So first of all, I want to see if there are other possibilities. And then if there is an 1107, then a second later, exactly a second later, I'm going to check to see, did I get a 2670? And if I did, then I'll check a second after that for a 5107 and a second after that for a 6670. If I get these 4 values in 4 consecutive seconds, then I know that I'm looking at I know exactly where I am within the frame. So the first frame, I might wait till 4 seconds till I see the first subcode. And from there, I know I have to wait another 3 seconds till I see the next 3. Only then do I know where I am and can I start recording. Now, when they wrote the original spec, they wrote the number, 1107, and this is octal. But what they didn't write is which bit comes first, the 1 from the 11 or the 7. In other words, does it go from left to right or from right to left? And obviously, whenever you leave something vague like that, half the people interpret it one way and half the people interpret it the other way. And that's in fact what happened. And so now most of the new hardware built just accepts either one of them on a receive. Okay, now to make life interesting, we said before that again there are 2 issues on every bus that you have to discuss. One is, how do you know there's only one transmitter? Well, 717 is easy. There's only one transmitter. The second thing is, how do you distinguish between a 0 and a 1? And there are a lot of different ways of doing this, and ARINC-717 chose 2 of them. So when you're buying a piece of 717 equipment, you got to ask the question, do you work in Harvard biphase or do you work in bipolar return to 0? Because if the equipment that you're connecting it to works in the other one, it ain't going to work. Let's look at what they are, just to give you an idea. Harvard biphase says that a 1, I know that a 1 is a 1 because in the middle of the bit, it changes, right? Now, it could change by going up or it could change by going down. In the first box, we see it changes by going up. And actually, in the second box, it also changes by going up. But if we go down to here, I don't know if you can see my cursor, but up here on the second to last bit, it's going down. But that also is a 1. Because if you look at the 0 boxes, they don't go up or down. They're the same for the entire length of the bit. So that's their definition. That movement in the middle of a bit is a 1, lack of movement is a 0. Now, bipolar return to 0 is familiar to us from 429, because in fact, that's what 429 uses. The idea being, bipolar means it can go either up or it can go down, and return to 0 means that between bits, it always is 0. So this line here in the middle, it gets there between each bit, as in fact you see it does. So that's the other method of indicating a 1 or a 0. Okay, now data rate is, so the original spec said that there are 64 words per second, right? We've been talking till now about frames. There's 1 subframe per second, a frame every 4 seconds, and there are 12-bit words, but we didn't talk about how many 12-bit words. And the number of 12-bit words is going to determine how long it takes for a bit. Right, because if I've only got 64 12-bit words per second, so a second divided by 64 is a large number. relative to the kinds of things we're talking about, and I'll have long bits. Whereas if I want to fit 1,000 words into the same second, then I only get, about 10 microseconds per word, which means I get less than a microsecond per bit. So the original spec was 64. As the planes got more complex and they wanted to have more data recorded, because there just was more data to record, they kept on upping the ante to the point where the Airbus 380, one of the more complicated planes in the sky, now puts out 1,024 words per second. And obviously 2048 is coming soon. Now, each time you add the number of words, you also change the spec to determine what are you putting into those words. So the original spec actually tells you what to put into the 64 words, but it didn't keep up. And now the Airbus on the 380 defined its own use for the 1,000 words per second. Okay, so in order to monitor it, you need to know what you're up to, right? Which subframe you're in and which frame. And then you use the spec of the manufacturer to tell you what each word actually means. Now, most cards that do the monitoring will give you a time tag. And the time tag, there are two types of time tags in common use and in our cards. One of them just starts at 0 on power up or on reset and counts in whether it's microseconds or tens of microseconds or where it happens to be. And that way you know the exact relationship between words. Of course, you know it anyway because it's a frame per second. You can also use an ARINC timestamp on words. In that case, you not only know what time it came in, but you also know relative to other things on the aircraft who might have also used ARINC, because they all get the same ARINC value. Now, ARINC itself really only puts out, ARINC basically puts out a mark once per second with extreme accuracy, but only once per second. So what we've done in our cards is that we take that mark, and from that mark, we start a microsecond counter from 0. And then we give you both the, what ARINC gives you, which is the day of the year, and the hour and the minute and the second, and we add to it the microseconds into that second. Okay, so that's 717 in a nutshell. Happy to answer questions either right now or email them in. As always, I recommend that if you're starting a new project and you'd like some advice on anything having to do with communications, give us a call. We're happy to help because we enjoy learning about the kinds of projects that our customers are involved in. Thank you very much.
Okay, thank you. Anybody have any questions? If not, thank you everybody for your chat messages. We have other courses. If you are interested, please be in contact with us, and tell your friends. Tell them we do weddings and birthday parties as well. And see, David's laughing. But if you have any questions, feel free to contact us, and we'll be happy to answer them. Have a good day, everybody. Have a good evening, and we hope to see you soon.
Okay, thank you.
Pleasure. Okay.
Thank you. So, Daraba.
Akasha.
Okay.
Okay.